All right, so in this lecture, I want to go over number 16 here from worksheet 34. And you can see right here, we have a picture of what we're going to be talking about. This is a amusement park ride that's called the Rotor in this problem. It's also, I think, when I had seen it when I was a kid at the amusement park, they called it the Gravitron. And what the Gravitron did was you would go inside of this room, right? And like you would all stand along against the wall in like a circle, and this room would rotate, right, and spin, and then the floor drops away, and you're left like levitating, maybe not levitating, but against your back is against the wall, and you're able to just stay there without falling, right? Because the floor is is dropped down a foot or so. And so because the room is in circular motion, this is possible. So that's what we're looking at here. And you can see this guy is standing here and he's facing, the center of the ride. And then we have the view from above, and it says, you can see with this arrow pointing into the center, probably for centripetal force or centripetal acceleration. And it says there's an amusement park ride called the Rotor where you enter a cylindrical room. The room begins to spin very fast until at some point the floor beneath you falls out. Suppose that this room has a radius of 4.20 meters. Let's go ahead and start drawing. So on this blank sheet of paper up here, let's draw a picture of this room. I think that's going to want to do a circle. Okay, so something like this, right? And let's just label R 4.20 meters. Okay. And that the room rotates such that you make one revolution in 3.65 seconds. All right, so let's write that down. One revolution per 3.65 seconds. So a revolution is once around. And, okay, so this is, all right, so one revolution per 3.65 seconds. Okay, so we're good so far. Let's see what else we got here. The diagram to the left shows an occupant of this ride standing suspended next to the exterior wall of this ride. What will be your linear speed as the room spins at this speed? All right, so linear just means it's not rotational speed, right? Like something maybe in radians per second. So linear is just our normal speed that we like to calculate. And if we were to calculate that, we could say that velocity is equal to distance over time. And we know the distance to go around the rotor or around the amusement park ride is the distance around a circle. So that's going to be the circumference. And we know the time to go around once is 3.65 seconds. So we can find the linear speed here just using this formula. Let's go ahead and plug in the radius. And then now we just got to do a little math here. Let me grab my calculator. 2 pi is obviously about 6.28. All right, so on top I'm getting about 26.4. We're going to divide that by 3.65. 6.5 gives us about 7.23 meters per second. And if we double it and then add some, 14, add a little bit, maybe 18 miles an hour, 19 miles an hour, somewhere around there is how fast this room is spinning. Which doesn't seem all that fast maybe, but it is, right? Like, I know I was scared to go on this ride when I was a kid, and yeah. So anyways, but I don't think it was too bad, as long as you don't mind spinning in a circle, and that can be a little rough. All right, so the next question says, what is the magnitude of your centripetal acceleration, and how many G's is this? All right, so this is part B. So we just answered A. All right, so for part B, we want to know centripetal acceleration. We're learning in class, or we've learned in class so far, that centripetal acceleration, A sub c, is equal to v squared over r. We can go ahead and plug in that r from part A, which was 7.23 meters per second. Make sure our radius is also in meters, which is 4.20. Whoops. Let me, I noticed something. I forgot to square this. All right, 4.20 meters. So if we do the math here, squaring the top first, 7.23. It's giving us about 52.27 on top. Whoops. That's going to be in meters squared per second squared, divided by 4.20 meters. Gives me about 12.45. So A sub c is 12.45 meters per second squared. Okay, so let's try and separate these two parts. All right, so there we have it. Part B, there's our answer. Are we getting these right? We should probably be checking them with the worksheet, but I can let you do that. On the back of the worksheet, there should be the answers to these. I think we're doing good so far. Now, it also said how many G's of acceleration. So if we have 12.45 meters per second squared as our acceleration, and we know that 1 G is worth 9.81 meters per second squared. And so we just do the math here. We can cancel off meters per second squared. So we just divide that 12.45 by 9.81, and we get roughly 1.26, 1.27 G's of acceleration. And this is also an answer for part B as well. So, okay, so we have, let's see, we have this answer for part B and this answer, and then this was part A. All right, so there we go so far. Hopefully that looks good to everybody and is making sense. Let's go to part C. Part C, on the diagram to the left, label all the forces acting on the rider. All right, so we're going to redraw this, but, you know, we'll make it look like the one on the left. So let me add a page here. All right, that works. So I think the diagram on the left, the one they're referring to, is the one where the person's standing there. And they are, they're against the wall like this. Okay. And the floor is down here. Something like this, right? Okay. So something I want to point out here, then let's free body diagram. And let's just think of what forces we would normally have here, right? So the first one would be force gravity. I think everybody would get that one. The next one would be what here? Force normal, but normal always points 90 degrees from a surface. And the surface the person is in contact with is no longer the floor, it is actually the wall behind them. So we're going to draw it 90 degrees to the wall, right? Which would be like that, right? Pointing that way. So let's go ahead and draw it pointed to the left. And we're assuming this person is facing the left as well. And then I think one more force, right? Because the person wants to slide down the wall, but this force isn't going to let them slide down the wall, and it's going to resist that, and it's going to point upwards. And this is going to be static friction. And do you have to write static? Probably not, but I'm gonna go ahead and include it. Because the person's not moving, right? I mean, they're rotating in a circle, but they're not moving relative to the surface. The surface is rotating as well. All right, so let's go ahead and go. Did we do everything? I think we did for part C. On the diagram to the left, label all the forces acting on the rider. I think that's it. I don't think we forgot any. Part D, what will be the magnitude of the centripetal force acting on a 50 kilogram person on this ride? All right. Let's go back here. Let's just write that down. Mass is equal to 50 kilograms, so I don't forget. And come over here. Centripetal force is the center-seeking force, and there's only one force here that's pointing into the center, and it occurs in the x direction, right? A lot of times I like to call, when I label directions here, I like to call into the center positive x. And so I guess this way would be negative x, right? If I was making my coordinate axis. I don't know why I drew it over here, but I did, so okay, whatever. I'm not really worried about friction and gravity at the moment. I'm just worried about the x direction. So once again, into the center is positive x. So let's go ahead and just do it like normal, right? Sum of the forces in the x direction equals max. We have one force here, and that's Fn, because it points into the center, positive x. The mass of the person is 50. And the acceleration, we know from earlier, we found that to be 12.45. And so what we're seeing here is that force centripetal is our net force, right? And we're seeing also that centripetal acceleration is our net acceleration. And I just want to point that out because that's how it shows up in these problems. Because you might be saying, well, why didn't we draw it on the free body diagram? Or I don't see it there, what's going on? This is how it's showing up. So it is showing up, and we know that AX is our net acceleration in the x direction, and we know that sigma Fx is our net force in the x direction. All right, so anyways, we do the math. 50 times 12.45, get our calculator going here. Get out of this green pencil. All right, 50 times 12.45 is about 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . 627 . And I just noticed that I went ahead and labeled this FM, and it is, but the problem I think asked for centripetal force. So I could just as easily have just kept it as FC because sigma fx is FC. So I'm just going to rewrite it one more time. All right, good. And this was this is part C, I think, or D? I think this is part D because I think C was drawing the free body diagram. So I think this was part C, right here, this picture here, and I think this is part D. Let's see. Yeah. Okay. And then part E, what will be the magnitude of the normal force acting on this person? Oh, we already did that, right? So part E and part D are the same answer, right? Because the normal force is the centripetal force. So the 627 newtons is our answer for part E. Okay. Let's go ahead and go back down. Part F says, what will be the minimum frictional force acting on this person? Okay. If we go, we don't know mu, right? A lot of times when we get this is part F. Let me write that down. All right, so a lot of times when we get a friction problem, we want to write this formula. But obviously we don't know mu, so that's not really going to help us. But if we just look at this free body diagram, we can see that the minimum frictional force that's necessary is to keep this person, from falling is going to oppose, or is going to be enough to oppose forced gravity, right? So the person's weight. So we can just show this just like we would starting a problem, equilibrium problem. Sigma Fy is equal to MAY. And what are we going to call which direction? If I go back over here where I had this, the x directions labeled, we'll call up positive y, and we'll call down negative y. And so we can go ahead and label those. Force friction static will be positive, and gravity will be negative. Mass is going to be 50 kilograms. Acceleration here. Now, into the center, it was 12.71 or 12.45. But in the y direction, the person's not speeding up or slowing down, so their acceleration is going to be 0 in the up or down y direction. So coming back to this, let's go ahead and label AY. All right. I think you can see where this is going. Right, and so force friction static, we'll just add Fg to both sides. I should probably show my work for this because I think some of you guys prefer that. I know some of you don't. Some of you are like, why does he write everything? But I can't make everybody happy. All right, so force friction static is equal to Fg. Fg is always mg, so let's go ahead and sub in mg for that. And if we do that, we can say Ff static. Could have just called it force friction, but we're being a little more descriptive. 50 kg times 9.81. It's going to be about 490.5 newtons, which is the minimum static frictional force to keep this person from falling. Now, a lot of times on these gravitrons, if I remember right, because I think I wrote it one time, and I can't remember though. I just remember it being really scared of it. So anyways, I think when I rode the gravitron, or when I was a kid and I saw the ride, that it looked like a spaceship, first of all, and I'm trying to draw the incline, right? It wasn't straight up and down like this. Instead, it was more like, let me see, it was more like this here, right? Like the person was laying back like this, and that way, it wasn't as scary, right? And if you think about it, why would this be? Well, if you do it this way, then your normal force points up like this, and friction points this way. You still don't want to slide down the incline, and gravity points, I was about to point gravity down the incline. Oh, terrible. All right, points straight down. And if that's the case, so what we can see here by tilting it then is that less is going to be required of friction, right? Because if we split force gravity into a piece of force gravity that goes down the incline and a piece that opposes force normal, you can call this FGY. I don't know why I used that real bright green. It's kind of hard to see, at least for me. But you can tell that friction only has to overcome FGY now instead of all FG, which is obviously the hypotenuse of this triangle on the longest side. So less friction is required on the gravitron when it's tilted at an angle like this right here. Now, how does this affect force centripetal? It obviously has an effect. Kind of difficult, or kind of hard to say, to be honest. I think you would have to go with some kind of normal axis system if you want to know how it affects force centripetal. Force normal would have to be split into parts like this, and you would have an FNX like that. But it would also be getting opposed by friction slightly, right? Because you'd have a forced friction in the X direction and a forced friction in the Y direction. So it's kind of hard to tell there. Seems like force normal would also be larger because obviously the surface can do more, can push back harder the more tilted it is. So it's a little trickier to see with how exactly that's going to affect force centripetal. But the idea being of tilting the gravitron or having you lay back slightly when you ride the ride is that, like I said, friction doesn't have to work as hard. So you don't need as much friction for you to stay in the air, and it's safer, right? So my guess is that's why there's a slight tilt to it. Because I'm pretty sure that's the way the ride actually works. But you could have it just vertical too, and that's fine too. All right, so to end this problem, let's do part G, and I think that's all that's left. It says, what will be the minimum? So in part F, we found the minimum frictional force acting on the person, which was 490.5. Now we want to know what is the minimum coefficient of friction between the rider and the wall. So this is just using our knowledge that force friction equals mu Fn, like we said earlier. We can rearrange this to solve for mu. So we'll just solve for mu equals force, friction, static over Fn, right? And do I have enough room here? I think I have enough room here to write this just right here. All right, so force, friction, static, we said was 490.5. Hopefully you can see this just fine. And force normal, we said was force centripetal, which is our 627 newtons. And let's go ahead and just, this is going to be mu static. I just don't like how all this looks like it's blending into the other problem, so maybe I can draw a line here to separate this. Let's see. Something, I don't know. Just something to kind of keep this separate. Okay, that's decent. So mu static, plugging this into the calculator. Notice newtons cancel, mu is unitless. We should get about 0.78. That would be the minimum mu static required, because you could always have a greater mu static, but that would be the minimum so the person doesn't fall. Okay, so there we have it. I hope all of our answers check out. I think they should. We can go down and look, highlight some of these real quick. I think this was part G at the end. I should probably label that. So I'll let you do the comparing here. Let's see. Whoops, went too far. So right here, we just did problem number 16. So see if those answers check out. You can hit pause there. And hopefully you can see all that. And because I know sometimes my screen cuts some of this off and it's hard to see. I think we had 627 for parts D and E, but that's okay. It's close. Why the difference? Because of significant figures and rounding is what they're doing. All right, so 0.788. I think we had just 0.78. Anyways, that's it. Have a good day.